It's 2 p.m., which means the podcast just started just now. Like, it's on a timer. So that means I got to get started, or else there's going to be a video of me, like, screwing around. I don't know if any of you guys have checked out the video. I watched it. It's pretty cool. I can, see myself teaching. I've never actually seen myself teach before. It's kind of instructive. I didn't realize I make so many freaking typos. I gotta watch out for that. I strongly encourage you guys to point out any mistakes that you think you catch. Like, I made a few stupid ones, like I misspelled acceleration, which is kind of not a very important mistake. But if you guys think you spot something non-trivial, definitely, please, I encourage you to speak up. Don't be shy about it. Maybe you're wrong, and maybe it's just a question, in which case it's probably a question that other people have too. But also, if there's students that I notice like regularly participate and point out stuff on the board, that kind of endears you to me. So I almost want to be like, if you can find mistakes that I make on the board, then that's worth extra credit or something. I mean, it's not actually worth extra credit, but I will definitely keep you in consideration when doing grades at the end of the quarter. So yeah, speak up. Don't be afraid to speak your mind and ask questions in this class. I have to say, being podcasted kind of raises the stakes a bit. Like, this lecture is going down in posterity, man. It's going to be on the internet. It's probably going to be saved forever. So, okay, all that said, what other announcement do I have is I've updated and clarified the homework policies. A couple students asked me about how many attempts you get on a problem. So I posted an announcement on TritonNet about this, and here's the policy. I'll just tell you guys, you get 100 attempts per problem, which is essentially unlimited. Well, I changed it to 100. Yeah, it's now 100, so I've changed it. Hey, guys. Yes.
I still don't have access to it because I'm not completely enrolled in the class, so I don't have I'm on the wait list, so I don't have access to it. What am I supposed to do?
Let's see. Send me an email. Okay, and that's for most of the problems except for the multiple choice. So for the multiple choice, you get 3 attempts. Unless it's just like a true or false, in which case you only get 1 attempt. Okay, any other questions before we get started? So today, it's a pretty big section. Well, go ahead. Okay, it's a pretty big section today. 5.7 is on substitution. So I better get into it because I don't even know if I'm going to finish this one. Okay, so the word substitution is probably familiar to you in math. Like you've done it before. For example, like in solving systems of equations, you might have to substitute one expression in place of another that it's equal to. And so now, obviously, this is a calculus class, and you only do a substitution when it helps you to solve a problem, right? So now, today, I'm going to show you how you can use it to solve integrals that up until now, like, you did not have a way to do. It's basically a trick that allows you to to solve problems And what it all really comes down to is the chain rule in reverse, right? Like everything you learned in 20A, we now learn in reverse in 20B. So this, in a sense, is the reverse chain rule. You can kind of think of it that way. And I gave you a whole bunch of homework problems on this stuff because really that's the only way you can learn it. Like I'll try and tell you some of the tricks today. You just have to do them, and it kind of comes down to experience, to being able to effectively use the substitution method. So I'm going to do it for both definite and indefinite integrals, and let's start with indefinite integrals. There's just one little thing I need to change at the end once we do definite integrals. So and let's start with an example. So how about if f of t is e to the t squared? Okay, then f prime of t by the chain rule will be e to the t squared times 2t. You know what? Let me just write the chain rule up here, just if anyone doesn't have it totally committed to memory, because it's super important. It says that d dx of f of u of x is equal to f prime of u of x times u prime of x. It is also sometimes written as df du times du dx. Okay, so the chain rule gives us that this is f prime. And I said we're going to do the chain rule in reverse. So it follows from the fundamental theorem of calculus that if I integrate this, I should get back to this, right? The integral of this quantity right here, 2t e to the t squared dt, is, well, we already know what the antiderivative is. I just calculated it. So that's e to the t squared. And don't forget plus c. Okay. Not so bad. Let me kind of make this example a little bit harder to sort of drill the point home. Similarly, how about if, here, let's say g of t is e to the t to the fifth plus t cubed. Then g prime of t, it's going to be, we'll get a 5t to the fourth plus 3t squared times e to the t to the fifth plus t cubed. So if we integrated 5t to the fourth plus 3t squared times e to the t to the fifth plus t cubed dt, we should just get back to the original function. And plus c. Okay. Now, in both of these two examples that I just did, we kind of started off already knowing what the answer was. And the whole point of this lecture is, what do you do when you don't already know what the answer is? How can you sort of recognize, how can you look at an integrand? Like, what if I started the problem by giving you this quantity right here and said, what's the integral? How would you figure it out then? And in order to do that, let me first kind of introduce some new notation. This is the notation we use in substitution problems. You might have heard the phrase U substitution, because for whatever reason, we usually use the letter U as the substituted variable. So let me introduce this U substitution notation. We've all seen that if U is some function of x, then U prime of x is also written du over dx. Question, is this a fraction? It looks like a fraction, but it's not technically a fraction, right? What it means is the derivative, which is defined in terms of a limit of fractions actually, but not technically a fraction. But for the purposes of integrals, you can treat it like a fraction. And I'll show you exactly what I mean by that. What I mean is I could multiply both sides of this expression by dx and get that du is equal to u prime of x dx. And this is basically what you're going to be substituting when you use substitution in an integral. So in this notation, the integral of f of u of x times u prime of x dx, we just said, according to the equation that I just wrote, where's my colored chalk? This guy right here is the same as du. So this whole thing, after the substitution, is the same as f of u du. That's what substitution does. I took a integral where it was originally in terms of x as the independent variable. And now there are no more x's appearing in this integral. It's now just all in terms of u. X is gone. That's one way to tell if you did it right, is you should not have any x's appearing anymore, anywhere. So let's say if capital F prime of u is equal to little f of u, and if u is a function of x, then according to this expression, f of u du, which is the same as f of u of x times u prime of x dx, is, by the chain rule, the integral of capital F prime of u du which is by the fundamental theorem, capital F of u plus c. Or if you want, capital F of u of x plus c. And this is how you usually want to write it. Like if you're originally asked to evaluate an integral where x is the variable, the independent variable, you usually want to write your answer the same way. And you could always check this by just taking its derivative and making sure you get back to the original integrand. So this is all really best drilled home by doing some examples. So let's see, what example did I choose first? Okay, how about cosine? How about cosine of x squared? So how about the integral of 2x times the cosine of x squared dx? Now, the first step in a substitution problem is to choose what your substitution is going to be. So let's look back at this equation right here. And let me give you a couple of examples right here. So i.e., if u of x is x squared, then du would be, you take the derivative and put a dx, so that's 2x dx. And you might have gotten the idea that that's exactly the substitution that I want to make here. So let u equal x squared. So du is 2x dx. And the integral, here, I'm going to write the 2x over on the end of it, just so like things are kind of more clear here. Why did I write it just in that order? Yeah, and you can see like the 2x dx is exactly what I needed it to be. That's the point. This right here is exactly my du. So the whole thing becomes, well, this just turns into a du, and we now write this, again, making the substitution as cosine of u. And hey, this is an integral we know how to do. Yeah, just the integral of cosine, that's no problem. That's, what is that, sine or negative sine? That's sine of u plus c. And as a final step, you probably want to put everything back in terms of the original variable, which was x. So let's write that as sine of x squared plus c. And if you're so motivated, it's probably a good idea to like take the derivative of this and just, as a check, make sure that it gives you this. So you can go ahead and verify that if you want. Yes?
du is not what you want it to be.
Yeah, then that just screws everything up, and you can't do this method. So it's kind of like, these problems are a little bit artificial in that they have to be specifically written in order for this method to be possible. And I'll give you an example where, like, even if you just mess up just a little thing, you can't do it anymore. But despite that, you would be amazed at, in practice, this is still an incredibly useful technique. And you still use it all the time. So yeah, despite that fact, you'll still end up using this all the time. And you will be surprised at just how many integrals now become possible. But OK, so I showed you the basic theory of it. I mentioned at the beginning of lecture that there's also a lot of tricks that go along with this. So let me start showing you some of these tricks. So in fact, let's take this same example, and I'm just going to mess it up in just a little bit, kind of like, what was your name? Yusuf. Kind of like Yusuf was asking about. Like, what if we didn't have just what we needed right there? So how about if I alter it slightly? Basically, I'm just going to take away the 2 for now. How about this guy? Yeah.
Oh, you know that x is 1/2 of 2x.
Oh, okay, yeah. So in this case, again, if we choose u equals x squared, so du is 2x dx. Once you calculate du, you look at this side of it, and you're like, okay, I need to get a 2x dx somehow in my integrand. What do I have? I could write this as, here, okay, so we've got the cosine of x squared. I've got an x dx. I want a 2x dx. So how about we just multiply and divide by 2? So I'll put here, how about a 2 here and a 1/2 here? Those cancel each other out, right? I can do that. But now I have exactly the du expression that I need. So this whole thing is 1/2 cos u du, which, again, we already know how to evaluate. So that'll be 1/2 sine u plus c, or 1/2 sine x squared plus c. Okay, that's that example. What's the next one? Yeah.
You don't have to distribute 1/2.
Yeah. It's a good point. So he was wondering if I should so technically, what was your name? Ernesto. Ernesto noticed, yeah, technically this is what I got. But then I just like kind of, I didn't put the 1/2 on the c. Should I have, or did I just screw up? Yeah, because it's a constant, so a half of a constant is still a constant. So yeah, it's a very good question, though. So yeah, let me just make a note. Okay, I got this example. If I whisper to myself, the podcast totally picks it up too. I noticed that. Actually caught myself cursing under my breath. Okay. Let's just do some more examples. So x to the third plus 78. Okay. Once you do enough of these u substitution problems, you'll kind of develop an intuition for doing it. So what, oh, sorry, hold on, let me finish writing this problem. This is to the 5th power. What does the intuition say your u should be here? I think it should be this thing inside the parentheses here. So let's try that out. And I say try it out because a lot of these problems you will find on the homework will involve some trial and error. You'll try a U, and maybe it won't work, and then you'll have to try a different one. And after so many, like I said, you'll just develop an intuition for it. So if I make this my U, which seems kind of natural to me because it cleans up this ugly thing right here, then du is 3x squared. Now I've almost got, 3x squared dx. I almost have a 3x squared dx. I just need to put the 3 in. So let's put a 3 right here and a 1/3 in front, and then the whole thing becomes 1/3 u to the 5th du, which equals 1/3, and this is quite easily integrated as u to the 6 divided by 6 plus c. So I get 1/18, and then finally, let's put everything back in terms of x. Okay. Not so bad. Let's continue on. The tangent one, yeah, that's a pretty good one. Okay, so I'll do a trig example now. The trig identities are very helpful in doing this, and especially the trig relations. So how about this guy? How about the integral of tan theta d theta? I want to know if someone can guess the substitution to make here. It's not even obvious just looking at it. But yes. Oh, okay, because we could rewrite this as sine theta over cos theta d theta. And what was your name? Emily said, let's try u equals cos theta. Oh, and I just want to point out, sometimes there might be multiple correct substitutions that will allow you to do it. In this case, if u is cos, then du is sine theta d theta. Negative sine theta d theta. And so here, how about let's put a negative in front and then a negative right here. And this whole thing right here is my du. So I get negative du over u, which again is nice and integral. That's log u. So I get negative log of plugging in back in terms of theta. Or we could write that as secant theta. You might notice, in fact, let me just point this out. You could now integrate any power of sine as long as there's a cosine at the end. You can now integrate sine to the n theta as long as there's a cos theta d theta at the end. So we just figured out a whole bunch of integrals we can do now. Yes?
What happened to the negative? Is it because it's a trig identity?
I absorbed the negative into the log, which is the same as log of 1 over cos. Remember that, yeah, the log of a negative ln x is the same as ln of 1 over x.
Yeah.
So log, so yeah, and then 1 over cos is secant. So we can now integrate anything of this form and also anything of cos to the n theta times sine theta d theta, where n is any integer now. So yeah, the amount of things that you can now integrate is rapidly getting larger. What examples next? Oh, okay. So here's another. God, I wish I could ditch all these like teeny nibs of chalk that are impossible to write with. Okay, here's another one where it's kind of tricky. Like, you probably wouldn't know how to do this one until you've seen the trick. So how about the integral of x times the square root of 2x plus 3? If you have some experience with substitution, your intuition will say, let's try and clean up that square root. So basically, let's just make whatever's under the square root sign, let's make that our u. That's going to be u. And then du is pretty simple. That's just 2 dx. Okay. So what happens here? I've got an x. I've got a square root. So I'm going to replace this with a u. By the way, from this expression, I can write that 1/2 du is equal to dx. So let's put a 1/2 du. But yeah, I think I heard someone like protesting. This is not, did I make a mistake?
No.
Okay, so this is not good though. What's the problem? I got an x. So what could I do? Yeah, I can solve this expression for x, actually. So from this, I can get that u minus 3 over 2 is, so let me just say what I just did. The trick here is to solve u equals 2x plus 3 for x, which gives x is equal to u minus 3 over 2. And then we're going to plug that in. Plug that in for x right here. So let me do that over here. And we get, what was it? U minus 3 over 2 times the square root of u, and we had a 1/2 du. Okay. So let's pull the 1/2s out in front. That's u minus 3 square root u du, which is, well, before I go further, like, did I make things better? Does this look integrable? Does it? This does look, or it will in a second, like something that you guys should know how to integrate at this point, because if I distribute the u here, so I'll just do this in 2 steps. U root u minus 3 root u, which is, hopefully now you recognize This is u to the 3/2 minus 3u to the 1/2, which we can integrate using the power rule. So that's 1/4 u to the 5/2 times 2/5 minus 3 times u to the 3/2 times 2/3. Did I do that right? All right, plus c. And let's just put everything back in terms of x's. So 1/4, what was it? 2x plus 3. 2x plus 3 to the 5/2 times 2/5 minus, let's cancel these 3's. I guess I could cancel these 2's if you want. Whatever, here. Okay, let me just finish writing this. Okay, so this is 2x plus 3 to the 5/2 over 10 minus 2x plus 3 to the 3/2 over 2. We good? Okay, yeah, I think it's all right. Yes? Oh, plus c, thank you, yeah. Yeah, good call. So, yeah, so this was one, just take note of the trick. You'll have to use that. All right, I think it's about time we hit definite integrals in our last 10 minutes. There's only one kind of real new thing to keep track of, which is now the limits of integration. And I'll just write the formula down. The thing with definite integrals is actually you kind of have a choice. So, okay, here's the definite integral u substitution, which says the integral from a to b of f of u of x times u prime of x dx is, as before, f of u du. And what needs to change is the limits. I shouldn't just leave them as a and b, right? Because a and b were x values, right? This integral started at x equals a. I could even write that, like some people even write the integral from x equals a to x equals b. But we got rid of x. X is sayonara. Like there is no x here anymore. It's all in terms of u. But we know what u is, right? U is u of x, so we should start it at u of a and u of b, whatever those numbers are. So let's see, what example do I have first for this one? How about the integral from 2 to 4 of x over x squared plus 1 dx? What's the right substitution for this guy? The denominator, yeah. That'll clear things up. So let's let u equal x squared plus 1 to get du is 2x dx. Right here, I've got a, that's du over 2, actually. So this whole thing will be 1/2 du over u. If you guys caught that, I basically multiplied and divided by 2. Or I just replaced this by du over 2, however you want to think about it. But the real question here now is, what should the limits be? And I just told you, you plug in the original 2 limits into our substituted variables. So the bottom one was 2, giving us a new lower limit of 5. And the upper one was 4, giving us a new upper limit of 17. So we get 1/2 ln, this is a log of absolute value of u, as usual. Oh, sorry, no plus c. Evaluated from 5 to 17. So we get 1/2 log of 17 minus 1/2 log of 5, or 1/2 log of 17 over 5 if you want. And what I want to point out here is you don't actually have to change the limits. There's another way, a totally equivalent way, where instead of putting in new limits, you just put everything back in terms of x before you plug the limits in. So let me show you exactly what I mean by that. And it's totally going to be up to you which one you prefer. So the other way to do this would have been to write the integral of x over x squared plus 1 dx is, well, as we just saw, that's 1/2 the integral of du over u, where u is x squared plus 1, and du is 2x dx, which is 1/2 ln u. And what we do now is we plug back in terms of x, as in the indefinite integral case. So this is 1/2 ln of x squared plus 1. You'll notice I'm not bothering with the plus c because we're not going to use it for this problem because I'm talking about definite integrals. So let's put in the limits. Putting in the limits on this problem, they were 2 to 4. So here, I'm not even just going to write them here, but from here, it'll be from 2 to 4. And as you're going to see, we're just going to get the exact same thing. It's ln of 4 squared plus 1, which is 17, minus 1/2 ln of 2 squared plus 1, which is 5. So yeah, it's no surprise we get the same answer there. It's totally just a matter of preference, kind of which order you want to do the steps in. You'll find that for some problems it's more convenient to change the limits, and for others it's more convenient to keep the limits the same and put everything in terms of x at the end. And now for my final example, and wow, I'm going to finish on time. That's great. Maybe even early. So let me just show you what can go, how sort of delicate this can be if you don't have just the right terms, like how about the integral of x to the 5th plus 10x squared plus 1 to the 10th and 5x to the 4th plus 20x dx. So this problem, I obviously prepared beforehand. And like we've done before, let's just let u be, well, I was going to say the denominator. Let's let u be this thing inside the 10th power in the denominator. So that's x to the 5th plus 10x squared plus 1. So then du will be 5x to the 4th plus 20x. Oh, hey, what do you know? That's my numerator. OK, great, perfect. So we could do this problem, right? This is then du over u to the 10th, which is totally doable. But what if we didn't have, what if I just mess things up just a little bit? And how about let's make that thing on the top, I don't know, how about like a 21? That one little change just totally messed it all up. So you actually can't do substitution anymore. At least not this way and not with requiring some other tricks. Yes?
Is there supposed to be a dx?
Oh, yeah, thank you. Good catch. So yeah, messing it up just a little bit can totally mess things up. And in this case, we now can't do it. Sometimes I'll just write u sub if I'm talking about u substitution. Yeah?
So how, besides just plugging in a bunch of different values for u, how do you determine when it's possible to use u substitution?
Yeah, it's a good question. It kind of just comes with practice, really. Like once you've done a bunch of problems, you'll kind of develop an intuition for it. And probably at first, you'll do a bunch of ones where it doesn't work out. And then eventually, like with me, I can kind of just look at it and see like, oh, that's a u substitution problem. Like u substitution will work on that one. All right, well, I'm done.